Hey everybody, welcome to the second week of Molecular Modeling, or Molecular Modeling 2. What we're going to talk about in this particular section is going to be VSEPR theory and 3D models. So let's get right in. There's a lot to cover. First things first, VSEPR's basic principle is that your valence electrons around your central atom stay as far apart as possible to minimize any repulsions. And there are general rules. There's a good bit of them. So let's just talk about it. The first thing I kind of want to explain to you, though, VSEPR is just an acronym for valence shell electron pair repulsion. Okay, it's an acronym. Your Lewis structure shows 2D distribution of atoms and electrons, and then your molecular geometry or electron geometry or 3D shape of a molecule or your polyatomic ion, either or, they can be determined using VSEPR. There are some general rules, though, and I want to go through those, make it easy for you. You're going to consider double and triple bonds like a single bond. You're not drawing multiple lines for your double and triple bonds, okay? Because this is just an approximation as an extra electrons occupy space, but this allows a simplified model to be determined, or to help determine your general shape, right? So if there are two or more resonance structures and that can be drawn for a particular molecule, your VSEPR theory can be applied to any one of them. So our guidelines to drawing our VSEPR sketches: 1, draw the Lewis structure. You know how to do that. 2, count the number of outer atoms and lone pairs around the central atom. If we do that, if we count, I'm going to show you how we're going to use our chart. This is going to be your central atom. These right here are going to be your outer atoms. And so we're going to talk about AXE notation, where A is going to be your central atom, X is going to be your outer atoms, and then your E is going to be lone pairs of electrons on your central atom. For this particular one, we have none. So let's go on to the next one where I can show you how to use this AXE notation. We have AXE notation, and I know that we had a boron, there we go. There we go. That's what we have coming from our last slide. So what did I say? We have A is your central atom. Your X is going to be your outer atoms. And then your E is going to be your lone pair of electrons. There we go. So when we're talking about finding these, we're just going to determine our generic formula and match it with the molecular geometry. You're going to name your bond angles using your tables in your handout. And just remember, the lone pair of electrons occupy more space than bonded pairs. And that's important because bond angles are going to compress when the central atom has a lone pair. And that's going to change your shapes a little bit, and that's okay. We're going to get into that. But what I want to show you here is our generic formula and what we're looking for. Let me see if I can get me a different color pen here. Here we go. We have a generic formula and what we're looking for, and that's going to fall right here in this column. And you'll see I refer to it as an AXE notation. AXE notation, that's where that's coming from, okay? So if we're looking at this particular one right here, what is our AXE notation? Well, our AXE, your A is your central atom. You'll always have just one A. And then you have your outer atoms, which is your X. And we have, in this particular problem, 3 of those. So I have an AX3. And then our E is our lone pair of electrons. Now, if we go back over here, we remember that we do not have any lone pair of electrons on this particular structure. So what we're looking for is an AX3 notation. That's going to be right here. And so every answer that you need for this particular problem is all housed right here, okay, where you're looking for AX3, all the way over. All the answers, everything you need right at your fingertips. So if we're looking for an AXE notation, we found it by using this chart. Now, if we want to determine the molecular geometry for CH3Cl, now we did this CH3Cl for a Lewis structure last week. All we're going to do is we're going to say our A our X, our X, our X, and our X, and then our E would be lone pairs on here that we don't have. And so what are we looking for when we're actually looking on here? We're looking for an A4 on the generic formula. So if we go down to AX4, we have everything we need in the answers all right here. In fact, our hybridization, check. Our bond angles, check. Makes it super easy when you read this chart. Again, remember, you should print this chart and bring it with you to class, because while we're working with it together, it is very, very handy to have. And what you're looking for, if you're looking for your electron geometry, you see that that's going to be tetrahedral right here, right? And if you're looking for molecular shape, it's going to be tetrahedral. So let's just say we're looking for hybridization, right? And then we're looking for our bond angles. Literally everything you need. How many bonded atoms do you have? How many lone pair do you have? This is actually how you'll draw it. So if you see you have your AX4, you have your, what was it? BCl? I'm sorry, that was from the last one. Let's go ahead and erase that. Not perfect. I enjoy not being perfect. And I enjoy making you laugh at me while I'm doing this too, and I'm okay with it. So let's go back up here. We had a CH3Cl. That's what we were working with on the previous slide. And if we're looking for our CH3Cl, we want to draw the actual 3D. It's right here. We know our central atom is going to be a carbon, right? And then we know we have what we're going to call in the plane. And so we're going to have something coming and something going. And I know that because I'm looking right here. I don't care how these are labeled. They could be coming and going, or coming or going and coming. It doesn't matter to me. But I know that my Cl, okay, and I'm going to have my H, and my H. Now I have to remember I have to put all of my electrons on here, and we can go back to Lewis structure to count for those and make sure we're doing it right. But we know our 3D shape is going to be tetrahedral, and we know our bond angle is going to be 109.5. That's how we're going to get there. So in the second case, molecular geometry for a nitrite ion, which nitrite is NO2 negative. We see the sign right here, so we automatically know it's a polyatomic ion. And what happens with polyatomic ions, they need brackets, and you have to have their charge, and that's why you see it drawn like this. But your molecular geometry for nitrite ion, you're going to consider your resonance structure. Both show 2 outer atoms and 1 lone pair on the central atom. Let's find it on the chart. So we have an N, we have an A, right? Then we have 2 outer atoms, which is your A. Sorry, your A. Well, let's go. There we go. And then we have a X and an X. And then right here, we have an E. Okay? So our AXE notation is AX2E. Because there's only one. We're talking about pairs, right? Not anything else, just pairs. Just remember pairs. So AX2E is what we're going to look for on that chart. Let's just go find it. What do we have? We have AX, let's write it again. AX2E is what our actual notation was from our NO2 negative. All right. So AX2E, AX2E, AX2, is this 2? Where's 2? AX2E. See, sometimes you just have to look. So everything you want to know about it is all in between these lines right here. So if we find it on the chart, then we're automatically going to know that the shape that we're actually drawing it is right here. We know that it is a bent molecule. That means if it is not going to be linear, right? We have an N, O, right? So it looks like when we're doing our Lewis structures that it's going to be linear, but it's not linear because the lone pair, remember the lone pair cause stress, That means we're coming here and here. And if I go down here to my little eraser, love my eraser, I can get rid of this, and you can see what I'm talking about, how it's going to be bent, okay? That's just a little fresh into where we're going next. There we go. All right, so we know where our electron geometry is going to be trigonal planar right here. We know it's going to be bent. We know it's an sp2. We know it's 120 degrees. That's what we're talking about. When we want to draw it, this is the exact, shape that we're going to draw it, and we're going to get it taken care of just by looking at the actual shape. So let's talk electronegativity. Or just the polarity of molecules in general. Electronegativity is the ability of an atom in a chemical bond to attract electrons to itself. So your exception, again, remember, is hydrogen, because the electronegativity sits between boron and carbon. Fluorine is the most electronegative on the periodic table. The closer to an element it is to fluorine, the more electronegative it is. Of course, your exception is hydrogen, because it falls between boron and carbon. But carbon or chlorine, which is out of carbon or chlorine, which is more electronegative. Well, chlorine is more electronegative because it's closer to fluorine. So chlorine is more electronegative than carbon, and that's how we come up with that. So if we're talking polar covalent bonds, when two atoms share electrons in a covalent bond, they don't share it equally if one is more electronegative than the other. They kind of play tug of war. And when we say tug of war, it results in the more electronegative atom pulling the electrons more strongly toward itself. So it becomes the negative end, or the electron rich end. Okay. Now, since electrons spend less time around your outer atom, that atom becomes the positive end, or the electron deficient end. Now, one atom is negative and the other is positive. So the bond has two poles, like positive and negative ends of magnets. Now, this is called dipole, and bonds with a dipole, which are polar covalent bonds. Now, if we're talking nonpolar covalent bonds, the atoms with equal electronegativity share equally in a nonpolar covalent bond. So your electronegativity in a H2 bond, maybe, how are we going to determine between polar and nonpolar? Most excellent question I ask myself often. So diatomic molecules, we have equal electronegativity. There's no dipole, which means it's nonpolar. If we have different electronegativity, there is going to be a dipole, and that's going to make it polar. Now, let's say there are 3 or more atoms. Now, it depends on the individual bonds and overall geometry as to whether it's polar or nonpolar. So, polar bonds can polar bonds be put on a nonpolar if the polar bonds completely cancel out each other, and there are guidelines. Sorry for my confusion. Let's talk about those. So to determine your molecular polarity, first sketch your 3D shape, not your Lewis structure, but your 3D shape. You're going to determine your electronegativity for each bond on the central atom using your periodic table. You'll draw your dipole arrows. Now, carbon-hydrogen often is considered nonpolar because the electronegativity between them is so small. If dipole arrows cancel each other, then you have a nonpolar molecule. If the dipole adds up to a net charge, then it's going to be a polar molecule. All right, sorry about that. We flipped through too fast. So the question is the CH3Cl polar or nonpolar? Now, we determine the shape is tetrahedral with a 109.5 bond angle. Now, this is the sketch. So chlorine is closer than carbon to fluorine on your periodic table. So chlorine is more electronegative than carbon. So we draw the dipole arrow from carbon to chlorine. The carbon-hydrogen bond is nonpolar, so you don't need an arrow. Now, because the carbon-chlorine is polar, you have a net dipole, which makes the whole molecule polar. All right, valence bond theory. Now, what we use, this is just what we use to explain how various shapes result from the atomic orbital s holding the bonding and the